Alright, in this video we'll be going through Kirchhoff's current law. This is one of two laws that you'll be using in NCEA level 3 to solve your circuit problems. So in order to understand what Kirchhoff's current law is, we need to first look back at what current is, okay? So current, by definition, is the number of charges passing through a singular point in a circuit in a given second. So the number of charges passing through a given point in a circuit in 1 second, okay? And so therefore, intuitively, if we were to have a wire, okay, right here, okay, and if we were to select an arbitrary point right here, intuitively it makes sense that the current entering this arbitrary point is equal to the current leaving this arbitrary point, right? And so this is the underpinning idea of Kirchhoff's current law, okay? So Kirchhoff's current law is the algebraic sum of the currents leaving any node in a circuit is equal to 0, okay? And so mathematically, that looks like the algebraic sum of all currents is equal to 0. Now, just a reminder on what a node is, okay? A node in an electrical circuit is a point at which two or more components are connected together either directly or via an ideal wire. And so if we were to have a component, let's say right here, and let's say another component right here, and the circuit goes off in both directions, in all directions, okay? We can see that these two components are connected together via a common node, okay? So this right here would be the node that they're connected to because they are connected via an ideal wire, okay? And so coming off that, what Kirchhoff's current law basically says is that if we were to have a junction right here, like so, okay? We can see that this is a node because we have two or more components connected together via an ideal wire, okay? So this right here is a node. And so therefore, the algebraic sum of all currents leaving this junction or this node is equal to 0, okay? So I1 plus I2 plus I3 is equal to 0, like so. Now, a common question is how do we know if a current is leaving or entering a node? Okay, we don't have to worry about this because a current entering a node is equal to the negative of the current leaving the node, okay? And so if we assume all currents are leaving the node, the algebraic signs will take care of themselves and we don't have to worry about them. Now, Kirchhoff's current law is so intuitive that you have been doing it your entire high school career, right? It's been ages since you first learned about parallel circuits, but if I draw a parallel circuit right now, okay, like so, like this, there we go. We know that in a parallel circuit, current is going to flow through here, okay? And we know when it gets to this junction, it's going to split. Some of it's going to go this way and some of it's going to go this way. Let's say both of these resistors have the same resistance, okay? Same resistance R. This means that the current coming through here will be I divided by 2, and this one will be I divided by 2 also, okay? Because they have the same resistance. And so, like I said, current is going to flow through here and then be split off at the junction. Okay, split off at the node. And then the currents are going to flow through here and through here. And so this is still I divided by 2, and this is still I divided by 2 right here. And we know they're going to join back up and come back to I, like so. And so if we define currents leaving a node as positive and currents entering a node as negative, we can see we have current I exiting the node, so that's positive, and then minus half I, and then minus half I again, because these two are entering this node, okay? And that's all equal to 0. And so therefore I is equal to half I plus half I. And so I is equal to I. And you can see that you have been applying Kirchhoff's current law this entire time. We can run through some more examples of Kirchhoff's current law. Let's say we have a situation where we have a resistor over here and a resistor over here, okay? If we were to have a current entering here, let's call it I1, and a current exiting here, let's call it I2, okay? We can see here that the current is entering the node and this current is leaving the node, and so therefore I2 minus I1 is equal to 0, and therefore I2 is equal to I1. And as you can see, we know this is true because these components are in series, and so we know that their current should be the same. And once more, this is a situation where you've been intuitively applying Kirchhoff's current law. Alright, let's work through a example with numbers now, okay? Let's say we will have a node over here with a resistor like so, and we'll have a central node with another resistor coming off like this and like this and like so. We're going to have negative 2 amps leaving, we're going to have 8 amps leaving here, and we're going to have 4 amps entering here. And what I want you to do is find this value I0. So you can pause the video and try that yourself. So in order to solve this, we need to find the algebraic sum of all currents leaving this node in the middle right here, okay? And so therefore, we have 8 amps leaving, so we can put that as positive 8. We have 4 amps entering this node, okay, so that's minus 4. We have negative 2 amps leaving, and so that's equal to 2 amps entering, okay? And so therefore that's negative 2, okay? And we have I naught, which we're trying to find, and that's leaving, and so that's positive, okay? And that's all equal to 0. And so therefore, this right here is equal to negative 6, okay? And so therefore 2 plus I naught is equal to 0, and therefore I naught is equal to negative 2 amps. And so we have a negative in this case, and so what that means is that in reality, I naught is not leaving, it's actually entering, okay? And that's equal to 2 amps, okay? All right, and that is Kirchhoff's current law. See you.